Hi everyone, welcome to lesson 4 in the fluids chapter. This lesson is on Archimedes Principle. In this lesson, we are going to define what Archimedes Principle is, and then we're going to apply and use Archimedes Principle to calculate the buoyant force and the apparent weight of objects that are in fluids. This lesson is almost a continuation of lesson 3, where we have to use some of the key ideas of buoyant force and displaced fluids to understand Archimedes' principle. So here we go. Just to state Archimedes' principle. Archimedes' principle says any object completely or partially submerged in a fluid is buoyed up by a force whose magnitude is equal to the weight of the fluid displaced by the object. So there's a lot there, and I want to try to underline or highlight some key points here. First off, any object that is completely or partially submerged. So as soon as you put an object in a liquid, you get a buoyant force. And the key to Archimedes' principle is this: the magnitude of that force is equivalent to the weight of the displaced fluid. It doesn't have anything to do with the weight of the object. It's how much fluid you displace. So take a look at this image that we have here to better understand Archimedes' principle. On this scale, we have a 7-pound object. When we place it into the water, what we find is that 3 pounds of water was displaced. It had to be moved somewhere else. Archimedes' principle says that the buoyant force will be equal to the weight of the water that was moved, to the weight of the liquid that was moved. So, because 3 pounds of water was moved out of the way, the buoyant force will be 3 pounds. 3 pounds buoyant force. If we moved more water out of the way, then we would have a larger buoyant force. So one of the key things to understanding Archimedes' principle is to understand how much the weight of the fluid that you're moving. So this is some of the important volume conversions that we have, and the most important one I would like to highlight is the second one. But basically what this says, the first one says, is that 1 milliliter of water is equal to 1 gram, which is equivalent to 0.0098 newtons. But the second one is even more important. 1 liter of water is equivalent to 1 kilogram of water. If you had a liter of water in let's say a container that was 1 liter volume, it would have a mass of 1 kilogram, but more importantly, it would have a weight of 9.8 newtons. That means if you can somehow submerge something that's 1 liter, a little picture here for you. If something has a volume of 1 liter and you put it in water, this is H2 water, and has a volume of 1 liter. 1 liter of water had to be displaced, had to be moved somewhere else. We know that because we displaced 1 liter of water, the buoyant force would be 9.8 newtons. One of the best ways to start understanding Archimedes' principle is through practice and through examples. So I'd like to do a couple examples with you right now. Here's the first question. It says, a 1 liter container of mercury has a mass of 13.6 kilograms and weighs 133 newtons. When it is submerged in water, what is the buoyant force on it? Is it A, 1 newton? Is it B, 9.8 newtons? Is it C, 13.6 newtons? Or is it D, 133 newtons? Take a moment and pause the video and try to figure out what you think the answer would be to this question, and then I'll go through it with you to practice Archimedes' principle. Okay, so hopefully you have a chance to pause the video and maybe come up with an answer. So let's look at this for some key points. It's a 1 liter container of mercury. That's important because that's going to tell us how much water is displaced by this object. It's submerged in water. Now the mercury part is a little odd because we haven't really dealt with mercury, but the only thing that's really important is this. If we're submerging a 1 liter container in water, we're displacing 1 liter of water, and the weight of 1 liter of water is 9.8 newtons. And that is the buoyant force. Buoyant force is 9.8 newtons. That's how much water was displaced. That's the weight of the water that was displaced, and that's the buoyant force. It doesn't matter what the weight of the object is. Let's try a second example. 3 blocks are submerged in water. Which block will have the greatest buoyant force acting on it? Is it A, the small yellow one, B, the mid-sized blue one, or C, the large orange one? You can also choose that all buoyant forces are equal, or there's not enough information to answer this question. So pause the video, take a moment, and see what you come up with, and then I'll go through the answer. Okay, hopefully you had a chance to pause and do the question. The correct answer is C. Object C has the greatest buoyant force acting on it because it's the largest volume object and it displaces the most water. And because it displaces the most water, it moves the biggest volume, which has the biggest weight of water, and that would be the largest buoyant force. Okay, final 2 questions. Here's the last multiple choice. Which block will experience the greatest buoyant force? Is it A, B, or C? Or do they all have equal buoyant forces? Or again, do you have enough information? Pause the video and try this question. And when we come back, I'll show you what the answer is. So we're doing a question, and it says, which block will experience the greatest buoyant force? Is it A, B, C, or they're all the same? Not enough information. And the buoyant force depends upon the weight of the liquid displaced. Since each object has exactly the same volume, it will displace the same amount of liquid, and they each will have the same buoyant force. So the correct answer is D. All buoyant forces are equal. The final thing that I'd like to do in this lesson is show you how we can use this idea of Archimedes' principle to calculate what we call the apparent weight of an object in a liquid. So let's read through this example together. A 3 kilogram object has a volume of 2 liters. If the object is submerged in water, what is its apparent weight? Or how heavy would it be if it were in the water? So first off, let's find the weight of the object, just in air. The weight is m times g, and whenever we want to find the weight, we multiply by the acceleration due to gravity. So the weight is 3 times 9.8. The weight of the object comes out to be 29.4 newtons. Now, when we place it in water, two liters of water is displaced. What is the weight of 2 liters of water? Well, 2 liters of water has a weight, 1 liter of water is equal to 9.8 newtons. So 2 liters of water would be 2 times 9.8. That would be 19.6 newtons. So our buoyant force is 19.6 newtons because we have displaced 2 liters of water. 2 liters of water has a weight of 19.6 newtons, and that's our buoyant force according to Archimedes' principle. Finally, what's the apparent weight? Well, if I do a little diagram here, here's our object, there's some water. We know that the weight is 29.4 newtons. The weight vector going down is 29.4. We know that the buoyant force is an upward force. We know that from previous lessons, and it's 19.6 newtons. The overall force acting on this, or the apparent weight, the net force, is 29.4 minus 19.6 newtons, and we end up getting a value, the net force, of 9.8 newtons. So there's how we can apply Archimedes' principle to find the apparent weight of an object. So just to recap, the most important thing about Archimedes' principle is this. And I'll go back to the first slide just so you can see it one more time. The buoyant force is equal to the weight of the fluid that's displaced. And if we know how much fluid we displace, then we will know the buoyant force, and we can calculate the apparent weight, and ultimately decide, as we'll do in the next lesson, if objects will sink or float. So thanks for watching. You should complete complete the quiz at the end of for this lesson, and we'll see you for lesson number 5 soon.